Okay. Last time we talked about linear independence. We're going to continue with that. And next section we're going to talk about coordinates and bases. Do you guys remember what this sums up to? Should we? Yeah.
Isn't it 1?
How do you know?
I remember it sums to 2 if it starts from 0. So I figured it's 2 minus 1.
Okay. But how would you figure that out?
Well, it's a geometric series.
Okay.
So r is equal to a 1/2.
Mm-hmm.
Well, yeah. And then 1 over 1 minus r is the sum. Is the
If you start at 1, yes. Right, the general form is a r to the n, where n goes from 0 to infinity. Which, I mean, if it goes from 1, you can think of it this way. And it sums to a over 1 minus r. Okay. We're going to continue with 4.3, I think it is, linear independence. Dense. We're to do some important concepts. Let's see if we can remind ourselves here. Let V a vector space. How would you define span? Let's say S. This is a subset of V. How would you define, if I say S spans V, what does that mean?
Every vector in V can be expressed as a linear combination of the elements in S.
Right, for all V in V, we can write V is equal to some C1 V1 plus C2 V2 plus Cn Vn, where the C's are scalars from our field. So in particular, this is like a real vector space, meaning the scalars come from the real numbers. Then I can write any vector in this vector space V in this manner, and I can say S spans V. What would it mean to say that S is linearly independent?
An equation of the form C1 V1 plus C2 V2 all the way up to Cn Vn equals the zero vector only has the trivial solution.
It's only a trivial solution. C1 must be equal to C2. All of these guys must be equal to 0. What's the main consequence here? What does that mean? If such an equation has only the trivial solution, what do I know?
No vector in that set can be expressed as a linear combination of the others.
No Vi in S is a linear combination of the others. What can I say about any two vectors? Let's say another consequence, this is one of them. Let's say I have Vi and Vj in S. S is independent. Where I not equal to j. What can I say about these two vectors?
They're also linearly independent. They're not scalar multiples of one another.
Right, then Vi, Vj are linearly independent together when considered any side by side, and neither is a scalar multiple of the other. And which means I can't write Vi as some non-zero scalar times Vj or vice versa. Right, that would contradict that S is linearly independent. So remember, linear independence was also a way to sort of cut out redundancies. You pretty much don't want any vector in a set. If I want a set to be linearly independent, I don't want a vector in that set that can be constructed from all the other vectors that are already there. So we don't want any extra information. Okay? And again, these things, these definitions that I go over, whether or not I go over them, definitions are very important, and the consequences of the definitions are very important. Like these are the ideas that helps you with proofs. Right? So knowing how to compute specific examples is important, but also knowing definitions and what they mean, what they imply is also very important to do well. So you should always make sure that you're studying these things. Okay. And last time we proved some facts about linear independence, like if a set contains 0, the 0 vector of the vector space, when is such a set linearly independent?
It is never linearly.
It is never linearly independent. Okay, so 0 cannot be a member of any linear independent set. So if we know a set only has one element, that element better be non-zero, and that's when it's going to be independent. Things of that sort. So we spoke about a lot of facts that come from linear independence, and you should remember those. Let's actually let's look at some functions. Right, so that's the notation for the set of continuous functions on R. It is a vector space over R. With the usual function operations. Of plus and scalar multiple. Okay, so you can prove that by verifying all the 10 vector space axioms, but this is a vector space. So let's actually look at apply this idea of linear independence to this set. And basically, I just want to do some examples. Let this equals e to the kx, f2 equals e to the lx. So I'm defining two functions here, two functions of x. Means you can think of k and l are scalars. When, if ever, are these independent, linearly independent? How would you approach that problem? give you two random functions, continuous. Let's say I give you two exponential functions. How would you verify whether those are independent or not? Yeah?
Put them in an equation, a e
Put
to
them
the
in the
kx,
equation.
plus a e to the kx plus b e to the lx equals 0.
Yeah, so consider, let's say C1 e to the kx plus C2 e to the lx equals the 0 vector, which is the 0 continuous function. I can just think of this literally as the element 0, because that functions as the 0 vector for the continuous functions, f of x equals 0 for all x. Okay, how would I go about knowing whether that's independent?
Cases, maybe? K equals L, K not equal L.
Okay, so we have cases. 1, what if k equals L, and 2, if k does not equal L, okay? In case 1, let's say k equals L, what can I say?
You have a solution like C1 equals minus C2.
Yeah.
That's not
Then choose C1 equals 1, C2 equals minus 1, we get a non-trivial solution. Okay, so it's not linearly independent in this case. Right? So notice that this implies something like e to the kl and e to the kx and e to the kx are dependent. Also, any multiple of these, if I take m e to the kx and n e to the kx, these are also dependent, right? If I multiply them by any non-zero scalar multiple, or even zero scalar multiples, they're going to be dependent. Okay? What about if k is not equal to L? How do you examine that situation?
Can you just tell straight away that you can't, one is not a scalar multiple of the other?
How?
Just like visually, I don't know.
The only scalar that you would be able to multiply either by would be e to some power, but then by the law of exponents.
Oh, wait.
You wouldn't be able to find some e to a constant pattern.
Why not? How do you know?
Maybe we can ln both sides.
You can't take the log of 0.
Oh, right.
Oh, can you say that they're never 0?
We know that e to the kx and e to the lx on their own is never 0. In fact, e to any constant times x is never 0.
So that means C1 times some non-zero plus C2 times some non-zero are, when you say that they have forces,
What would that say?
forces,
We know they can't be 0. We also know they can't be negative by laws of exponents. But I can just choose C1 and C2, one to be positive, one to be negative. How do I know I can't choose that in such a way that I would get 0 if I have two different exponentials?
Because they can't be equal, because we said K and L aren't equivalent. I don't know how to phrase that, but if K and L can't be equal, in this
Sure,
case.
if K and L are equal, we already dealt with that
Right, but
case.
if they're
And I can
not-
just choose this. Choose C1 to be anything and choose C2 to be its negative. What if I change their values? What if I put like a 3 and a -3 or a 0.5 and a -17? How do I know I can't find pairs of numbers to make this 0? Maybe you're just not thinking of the right numbers.
If e to the anything is never 0, can we divide by it? You get like a ratio of.
We could divide by it. Let's, right? I mean, it's a real number. That's one of the first things you're going to see if you do. Maybe we can divide by it, or equivalently, let's factor out and divide by it. Let's say I factor out e to the kx. I would end up with what? C to e to the L minus k times x equals 0. This would mean e to the kx equals 0, which we know does not work, or C1 plus C2 e to the L minus k x equals 0. How do I know that C2 and C1 and C2 must be 0 in this case?
Comparing coefficients. Comparing, yeah, like terms. Like C1,
So-
e to the anything is never 0. Then C1 has to be 0, and C2, I mean,
You mean by comparing coefficients, like writing this as 0 plus 0 e to the
Yeah.
k minus L?
Yeah.
Right? Yeah, we could do that. We could also say something like, we know here that ce to the equals minus C1. And we can do something like assume the contrary, that C1 not 0 and C2 not 0. What would you be able to say? Oh, well, we have to say or. Right. So in this case, if my C1 is not 0,
then C2 can't be 0 either.
right,
So you
then C2 can't be 0 either. And so that means I can actually do what?
Well, you said one has to be only, well, both could be, I mean,
Right, C1 is non-zero, which means C2 cannot be 0, because if it were 0, I would get 0 over here, but I didn't. Which means I'd be able to divide by it, so I'd be able to write e to the L minus k to the x equals some constant, right? Which we know is a contradiction. It's not a constant function. Similarly, if C2 is not 0, this means, again, C1 cannot be 0, and you get the same contradiction. So tons of ways you can do it, but again, remember, you don't want to appeal too much to some familiarity that you know about. You want to be able to prove things in a fair amount of detail. So, in fact, we can make a general claim here. E to the kx and e to the lx are linearly independent if and only if k is not equal to L. Right? We proved this direction by the contrapositive here, and we proved that direction here. So we can say that. What about these functions? F1, F2, independent or dependent? all these functions are continuous on the real line. So they are in C infinity to infinity. Dependent or independent?
We have to check each one with each other, right, with the others.
Sure. Can we check them all at once? So what are you saying? We can check each pair, this with this with that, and then this with this. You could check it pairwise. Well, let's use the definition. If we look at this guy, equals a zero vector, which is 0. Do we have a non-trivial solution here? Do those have to be 0?
Are there any trigger identities I will have? Because I don't want to remember much of this stuff. It's bad.
Maybe. Here's a pitfall that I want to point out. Let's say we wanted to do that that trick where we sort of wanted to like equate coefficients or something. What if I thought of this 0 as 0 times cosine 2x plus 0 times sine squared x plus 0 times 1? Could I just equate coefficients here? That can kind of not backfire on you, right? So, which is why I didn't want to really take that suggestion here, because you knowing how to express 0 for any random continuous function can be somewhat problematic. We in fact know that these are dependent; they're not independent. So there is a non-zero solution, and it does come from a trig identity. If you look at the double angle form for cosine, remember what that is?
2 sine cosine.
1/2.
Sine squared x minus cosine squared x.
This is, well, the other way, cosine squared x minus sine squared x. Sure. Are other ways to write this one in particular?
1/2, 1 plus
Sorry.
x squared.
Yeah.
Let's try to rewrite it in terms of these guys we have here. So the cosine squared is not mentioned, so let's get rid of him. How can we get rid of cosine?
1
Rated
minus.
as 1.
Right, cosine squared is 1 minus sine squared. This actually is 1 minus 2 sine squared. Right? You can also think of it as 2 cosine squared minus 1, right? But in other words, what we've just, this is a trig identity, so that in fact means that if I take 1 times cosine 2x plus 2 times sine squared x minus 1 times 1, I will get the 0 function. It's a non-zero solution, therefore these are dependent. So we can find a non-zero solution. You can start to see that there are some challenges here when it comes to random continuous functions, and various vector spaces will present their own challenges. So say we can let's try to find some situation where we can actually talk about functions in a very simple, easy way, where we don't have to worry about these little nuances or worrying about remembering whether we can remember the trig identity or not to deal with the functions or some sort of other identity. Let's expand our view at the C to the C1 functions. Remember, these guys are the continuous functions that are once differentiable. Or just Cn. This includes the above examples, but of course many other functions. here's what I want you to realize will happen here. Say we have C functions that are at least n times differentiable. We have n functions all belonging to this guy. We actually don't need even this guy. We could even go one less, Cn minus 1, but let's say they live in Cn anyway. Now consider this equation. C1F1 plus C2F2 plus Cn equals the 0 function. Now I want to be able to easily find a solution to this in sort of a brain dead way where I don't have to memorize any identities or just see a special relationship working out or know specifically if the functions are always greater than 0, less than 0. I want something a little bit easier than that. Now, obviously something is going to be involved with derivatives since I have actually invoked this class of functions here. And so, what can you tell me if I went through and I differentiated this equation? What would happen?
You would have constants times times continuous functions that are differentiable n minus 1 times.
I would get that by differentiating once.
Those C1s are different, right?
Huh?
Are they the same?
No, they're the same.
Oh, they're the same, okay.
Right, by the property of derivatives. If you differentiate a constant times a function, the result is a constant times a derivative function. Right? I can go and I can differentiate twice. And I would end up with that. I can keep doing that. And I will stop at n minus 1. Now you might ask, why did I stop at n minus 1? Because it turns out then the coefficient matrix over here is going to be a square matrix. This means I have this thing going on here. F1, F2, Fn, F1 prime, F2 prime, Fn prime, all the way down to F1 to the n minus 1 prime, F2, n minus 1 prime, Fn, n minus 1 prime. Here's my C1, C2, C3, all the way down to Cn. These are the guys I want to find the solution for. I want to know if that's only the trivial solution. And I want to know it must be 0 in all cases. Now this is a homogeneous system. Turns out we know it's always consistent. So there's definitely some solution here when all our functions are continuous and differentiable. I want to know, is there only one solution? How can we know there's only one solution?
We could use different facts from the equivalence theorem.
Sure. What does the equivalence theorem tell us?
If that coefficient matrix is invertible, if the determinant is 0.
Let's use the determinant. It's a nice little thing. Find the determinant and finding something is invertible. The determinant is probably easier to get away with. But if I call this guy here A, I know that if the determinant of A is not 0, then we have a unique solution. Right? So the continuous functions I happen to be working with are at least n times differentiable. I can have a very nice little thing that I can check to know whether they're linearly independent or not. Just find this guy and set that equal to 0, or just ensure that that is never 0 at the same time. by the way. This guy actually showed up in differential equations. Anyone remember what this guy was?
The Wronskian.
This is the Wronskian, right? Named after the mathematician Wronski. I don't know if he was the first guy to recognize it, but he's who it's named after. The matrix A here is called the Wronskian. Of the functions f1, f2, fn. We can denote it by w parentheses f1 comma all the way up to fn. Right? And by the equivalence theorem, if the Wronskian, sometimes write W if understood. Just write W. If the Wronskian is not 0, this means we have a unique solution.
The Wronskian is the determinant, right, of the matrix?
It's determinant, yes. The determinant of A here is called the Wronskian. We know that if the Wronskian is non-zero, we'll get a unique solution, which means it has to be the trivial solution. Because we know that this means that the Fn are independent. That is, in fact, we can take this as a theorem. And you can actually prove that. There's a little trickiness here, though, that's because we're introducing continuous functions and they might have their own relationships going on. The converse is actually not always true. Or the inverse, i.e. knowing that the Wronskian equals 0 does not imply f1, fn are dependent. So someone actually came up with a counterexample to that. So our theorem here, if I just want to state a little bit more cleanly, that f1, fn be elements of Cn minus 1, then if the Wronskian of f1, fn equals w is not equal to 0, on I, which is some interval where they're all defined and continuous, then f1, fn are linearly independent. On I. So knowing that the Wronskian is not 0 automatically gives us linear independence. So here's an example. If we go back to that original thing that we had, e to the kx, f2 was e to the lx. Let's just assume that k is not equal to l. Then here I can say that the Wronskian would be, here's this function. I have two functions, so I want to differentiate it n minus 1 times, so I'm going to differentiate once. Come down here, This would be k e to the kx, e to the lx. Come down here, differentiate, this would be l e to the lx. If I find that determinant, it's a 2 by 2, I would have L e to the k plus L times x minus k e to the k plus L times x. This would be L minus k e to the k plus L times x, right? I know that this guy's non-zero, right, because I'm assuming k is not L. I know that this guy's never 0, right? So that means that this will never be 0, which means, according to this theorem, those guys are linearly independent.
I mean, it's maybe obvious, but a question, just to demonstrate there's a unique solution, why does it demonstrate that unique solution is 0, the trivial solution?
Because on the right side, it's all zeros.
Oh, okay.
And we know in a vector space, 0 times a vector gives us 0. So that has to be a solution by our properties of vector spaces. So you can do that. And oftentimes, worrying about this single expression is easier than worrying about a linear combination involving all the expressions, right? So you can use this guy to sort of condense this entire equation with a bunch of expressions with a bunch of coefficients into a single function using the Wronskian, and knowing about that function can actually tell you about whether the thing is linearly independent or not. A counterexample. The converse. It's due to piano. Same guy who came up with the axioms that define the natural numbers. You look at the functions equals x squared. This times absolute value of x. Turns out that these the Wronskian will give us 0 on any interval that contains 0, but it turns out that they're linearly independent on all such intervals. Right? So you have to be careful. So just know that this is a very important theorem, but you can only apply it in one direction. Knowing that the Wronskian is not 0 gets you to realize that it must be linearly independent. But if your Wronskian is 0, you don't really know. There could be another thing. There could be other options. It could be, i.e., if Wronskian equals 0, our functions may or may not be dependent. So you have to be a little bit careful here. So a lot of times in differential equation, you guys use this Wronskian determinant. This is kind of where it came from. The idea came from the equivalence theorem. Because derivatives is a linear operation, actually. It's a linear transformation. So linear algebra applies, and we can use the determinant to our advantage. problem. Let's say I give you these two functions. Show f1 equals sine x, f2 equals cosine x are linearly independent. So you could go about this directly, say c1 times sine plus c2 times cosine equals 0. And you might take the risk of saying, oh, just write that as 0 times sine plus 0 times cosine and equate coefficients, but that's kind of iffy. You don't know. Is there a trig identity that relates these two that I'm not remembering? You don't want to have to worry about that. So one way you can look at this is to actually compute the Wronskian. If the Wronskian is 0, you don't have any information, you have to do something else. But if it's not 0, we can definitely make a conclusion. So consider the Wronskian sine and cosine. This would be the determinant of, again, I have two functions. So I'm going to differentiate one's derivative of sine,
Cosine.
derivative of cosine, negative sine. So then this would be minus sine squared minus cosine squared, which is it's actually -1 for all x, which means not 0 for any interval. Which means sine x and cosine x are linearly independent. And because they play on each other, because one can differentiate and become the other one, back in differential equations, anytime you realize that one of these guys was a solution, you have to assume the other could possibly be a solution. And so you'd represent your solution as c1 times cosine plus c2 times sine, and you know that there's no redundancy in this because they were linearly independent. One will never be a multiple of the other, so they could be two legitimately distinct solutions, and their sum would be the general solution. That's a lot of background there. Let's actually move on. A lot of things in differential equation, it's straight from linear algebra. Because once you look at the differentiable functions as a vector space, and you look at the differentiation itself as a linear transformation, you are now in the space of linear algebra. And once you can construct something to get a matrix in there, you can use anything that works on matrices. You can use the equivalence theorem or anything else. And you can draw a lot of conclusions there. And we'll draw some more conclusions about differential equations later on. But for those of you who have taken it already, now you can think back and see, oh, that's what, oh, okay. Because you probably didn't prove it in differential equations here. It's not a proving class at this college. But you can go back and you can start to see why some of the things had to work out that way. Why does an nth order linear differential equation have to have n solutions? Things of that nature. It's all linear algebra, really, in the background. That being said, let's move on. We're going to talk a little bit more about differential equations later. I'll give some examples every now and then, but let's move on for now. We're going to talk about coordinates and bases. By the way, bases is the plural for basis. Just a little FYI. I also kind of mentioned what coordinates are. I'm going to remind you of that soon, but let's actually start talking about bases. Definition. Let V be a vector space. And SB a set of vectors in V. we say S is a basis for V if, does anyone know? What makes a basis? Yeah?
Vectors in S are linearly independent and they span S, they span V.
There are two things. S is linearly independent, meaning there's no extra fluff, right? All the vectors in S are super important. They have to be there, because if I lose one, I can't construct them from the other ones in S. So it's a minimal set in that respect. And two, S spans V. Meaning any vector in V, I will be able to write as a linear combination of the vectors in S. Let's look at some examples. I'm not sure if yes. But let's look at some examples. Okay, let's say V equals Rn. Define, and here I'm pretty much defining a notation. We use the notation E sub I to represent the vector 0, 0, blah, 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 0, 1, the number 1, 0, blah, 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 0, where these guys have n components. And this is the ith position. Right? So there are familiar examples, of course. If we talk about R2, then my E1 is specifically the vector I, my E2 would be the vector J. There's no E3 because I don't have space for it. Or in R, and this would be the two-dimensional I, 1, 0. This would be the two-dimensional J, 0, 1. In R3, my E1 would be the I, which is a three-dimensional I. E2 would be the J, the three-dimensional J. And E3 would be the K, which is the three-dimensional K. And so on. In R4, we don't have letters for them. So we'd call these the like E1, E2, E3, E4. Right, so this is the vector where there's a 1 in the first position, 0 is everywhere else, 1 in the second position, 0 everywhere else, 1 in the third position, 0 is everywhere else, 1 in the fourth position, 0 everywhere else. For Rn, the set S equals the set of all EI's such that I goes from 1 up to n is called the standard basis. For Rn. This is the standard guy. If we're looking at Rn, I can always use this guy as a basis. This is my brain dead basis if I have no reason to choose anything else. That's the basis I'm going to choose. That's the one that's easiest to work with because according to this basis, the coordinates of any point is itself in a notation speaking kind of way. But let's actually continue here. Standard in the sense that it's often used because it's the natural thing to use. How about basis though? How do we know this is a basis?
show the two things.
We gotta show the two things. Let's show independence. So if I take C1 E1 plus da da da, Cn En equals the 0 vector, which is just, let me write these as column vectors because I don't want to take a lot of space. 0, 0, da da da, n times. Basically what that means is I can rewrite this guy as a matrix for my C1 all the way down to Cn is here. And the guys in here, the vectors that would be here would be my E1, E2, E3 all the way down here. This would be 1, 0, 0. This would be 0, 1, 0. This would be 0, 0, 1, 0, etc. Right? You'll notice that there's nothing to reduce here. This already gives you In. Which means that my C1 through C2 all the way to Cn must be 0 because I get the In vector by just plugging into it. It's another reason why it's standard. It's really the brain dead natural thing to use because once you set up the equation, that's the answer. There's nothing to do. And 2, if you want to check span, all you have to do is let x1, x2, xn in Rn be any vector. I want to show that it is a linear combination of E1, E2, E3, E4, all the way up to En. Then I can write x1, x2, xn to be equal to just x1 times E1 plus x2 times E2 plus xn times En. So this is an independent set of vectors and they span the set. Therefore they form a basis. Because it's super easy to form a basis with these guys, it requires literally no calculations. It's called the standard basis. It's the easiest one to use. So that ends our first example. The set E1 da, 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 En is a basis for Rn, known as the standard basis. Let's look at another one. Let V equals Pn. Remember what that is? Pn. What does Pn represent?
Polynomials of degree n.
Or less. Right? We need less because when we start adding them together, we can kill certain powers and then we lose them. So that is the set of all polynomials with real coefficients of degree n or less. It turns out that it also has a standard basis. What would be the brain dead standard basis?
1x x squared.
1x x squared all the way up to xn. Right? Every polynomial I'll be able to express as some linear combination of those guys. What about the 0 polynomial? Why don't I include 0 here?
Wouldn't be linearly independent.
Right, we had a theorem that says if I throw the 0 vector in there, it's not linearly independent anymore. So 0 is not there. How can I get 0? Just set the coefficients to be 0. Right? So the vectors themselves, none of them can be the 0 vector, but if I want to get the 0 vector, just make the coefficient 0. And then we have a theorem that says that gives us the 0 vector. Right? So this is the natural way to do it. You can realize, and here you can start to do things like equate coefficients. So you think of this as 0 plus 1x. Think of this as 0 plus 0x plus 1x squared. Right? Then by taking their coefficients and thinking of them as vectors, if you throw them in a set, you end up with something like that happening. And so that's also the standard vectors for the set of polynomials with degree. So this is standard basis. For Pn, which is the set of polynomials of degree n or less. Let's look at another one. by n matrices. That's a vector space. They follow all the 10 axioms of a vector space with regular matrix addition and scalar multiplication. Can you tell me a standard basis for this guy?
You would have n by n total matrices in that set, and you would go component by component, setting each one equal to 1, and then the rest to be 0.
Alright, so 1 here, 0 everywhere else. Then I would have one where there's a 1 in the second part, and zeros everywhere else, etc. Right, so it's a set of all matrices where there's a 1 at any given time, there's a 1 in each component, zeros everywhere else. Say I'm looking at M22 just for me to write out a full set. What would the standard basis for this guy look like? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. I can take that as a basis for the set, meaning these guys are all linearly independent. You realize if I take C1 times this plus C1 set it equal to the 0 vector for M22. Each component would, if I sum them all, I've got C1, C2, C3, C4 equals 0, 0, 0, 0. Two matrices are equal if their components are equal. That gives you C1 all the way down to C4 equals 0. So that's independent. It also spans the set, because if I take a random matrix A, B, C, D, then A times this plus B times that plus C times this plus D times that gives me that matrix. Right? So that's a standard basis for M22. And you can do this for M3 or M7-3 or N whatever, right? Any size, any dimensions matrix. Those are just some brain dead examples. Oh, note some facts here. Bases are not unique in general. Right? So remember, I gave you two sets that spanned R3. Remember, two sets of 3 vectors that spanned R3. Turns out that both of these were bases. You can go back and check that each one spans and is linearly independent. Right? So bases are not unique in general, so that's something you need to know, which is going to be an important property. Switching from one basis to another is going to be a useful thing for us. There's actually a section on that called change of bases. So bases are not unique in general. Here's something that might come up, that might keep you up at night, even though technically I'm probably never going to test you on this, just for a general application. What is the basis of the 0 vector space?
Intuitively just say 0, but
You can't say 0, because there's a theorem that says it. It turns out we're forced to say the empty set here. Its basis is nothing. It's a set of nothing. Gives us the 0 vector space. And that's just to be consistent with our definition of what it means to be linearly independent. Here's another interesting fact. We often order bases, okay? So let S subset of V be a basis. We often write S equals V1, V2, n, where this follows some definite order. Right? Probably better expressed as a tuple, because tuples define order. But it's a set, but we impose our own order on it. Of course, there are some standard ways to impose our order, such as the E nomenclature that I introduced earlier imposes an order on I, J, and K for the vector space R3, right? I always think of the I vector as somehow the first vector, and the J vector as the second one, and the K vector as the third one, right? So technically it's just a set. It doesn't really come in an order, but it's often convenient to actually fix an order on it. So that when I'm in R3 and I write A comma B comma C, I know that A is the coefficient of I know that B is the coefficient of J, I know that C is the coefficient of K. I can know which basis vector is attached to which constant, right? So it's often convenient to actually order a basis. Now, when a basis is ordered, we gain a notion of uniqueness of basis representation. Meaning, every vector in a vector space, when expressed in terms of an ordered basis, can be done so in a unique way. Meaning, if they have the same representation in terms of coordinates, you can consider them the same vector. Right? And this is why, say in R3, you see the vector 1, 2, 3. That to you is distinctly different from 3, 2, 1, or from any other arrangement, because the order matters to us. Right? And so, if you're talking about 1, 2, 3, there's a unique way to write down that coordinate. Right? It's only 1, 2, 3. The moment you change the value of one of these coordinates, you're not at 1, 2, 3 anymore. You're somewhere else. Right? Because you can express this 1, 2, 3 in a unique way. Right? As long as the values the real numbers you're putting in here, the absolute values go to 1, 2, 3. You can only do that in a unique way. That is, if x is in V and S equals V1 to Vn is a basis, we can express x equals C1 V1 plus C2 V2 plus Cn Vn in exactly one way. Any other linear combination of x that uses these vectors V1 through Vn in that order will have to be exactly equal to this. Right? So my coefficients here have to be exactly the same. There's no other way using these vectors in that order with a different set of coefficients that will give me the same vector x. I can only represent x in terms of this basis in one way, only one way. Proof. Assume the contrary. Suppose x equals C1 V1 plus C2 V2 plus Cn Vn, and x is also equal to, say, D1 V1 plus D2 V2 plus Dn Vn. Here's the claim. C1 must be equal to D1, C2 must be equal to D2, and in general, Ci must be equal to Di for all I. The coefficients have to be exactly the same. They have to be exactly equal. How would you go about proving that?
Subtract the vectors.
Subtract them. Right? So call this equation 1, call that equation 2. Since if we take 1 and subtract 2, this means we get 0, right? Because I'm taking x minus x would be equal to C1 minus D1 V1 plus all the way down to Cn minus Dn Vn, which means
Since we were given that there was a basis
Mhm.
that has just one solution, the trivial one.
right. This is a linear combination of the v's, the vi's that give me 0. There can only be one solution here. Since S is independent, I should really say linearly independent.
Can we
Our
write Li?
C1 D1 must be equal to C2 minus D2 must be equal to Cn minus Dn must be all zeros, which implies that my C1 equals D1, my C2 equals D2, and my Cn equals Dn.
Can we write Li on the test? Or LD?
LD.
Linear, well, like in a case where it's linear.
I mean, just write it at the top somewhere. Just write it. In this test, ever you see Li, it means linear independent, and then go for it.
Okay.
Because I wouldn't want to do that myself. Basically what this means, if I take an ordered basis, the coordinates used to represent any vector according to that basis is unique. Now that is super useful. With respect to S, when it's ordered, the coordinates of the vector x, i.e. the vector c1, c2, cn, which is an element of Rn, is a unique representation of x. There's literally only one way to express x as a coordinate with respect to this basis. Now if I change the basis, there could be some other coordinate that represents x, sure. But with respect to that basis, there's only one way to do it. Bases aren't unique, so I can choose another basis and I'll get another coordinate. But as long as I'm using that, playing around with one particular basis, there's only one way to write a coordinate for every vector in that vector space. So define, and I defined what a coordinate was in a previous lecture, so you can just review that. I'm going to define a different notation here. Let V be a vector space, S a basis, and X in V. The coordinate of X with respect to S is denoted. I write X and I write a little s down. Let's change this S to a B. Because S is usually the natural thing that we use for a standard basis. We call it S. But in general basis, we usually call them B. Right? So you can talk about different coordinates with respect to different bases. And if you are working with several bases at once, and you want to talk about the coordinates of some vector, you should be identifying coordinate with respect to which basis are you talking? Let's briefly talk about some implications of this. So here's my vector space V. Okay. And I have some x vector living in V. I have some basis that I can write the coordinate. So let me think of that as a function. Express x in with respect to basis B. It means somewhere over here in the set Rn, there's going to be a coordinate that relates to that vector. And it turns out that that coordinate has to be unique. That will be the only coordinate that relates to that vector, right? Which meaning if I say some other vector that's not equal to that will be mapped by that same basis to some other coordinate, say d1 through d1, right? Each x in my vector space will be linked to exactly one vector in Rn, right? This relationship will be one-to-one and onto. Right? That's something we'll justify later, but I'm just going to tell you right now. Right? Each vector, I can link it uniquely to a coordinate in Rn. Right? Assuming that V has a basis that has n vectors in it, I will be able to link it uniquely to a coordinate in Rn, which means this guy and this coordinate are interchangeable as far as I'm concerned. They'll always be the same guy, right? This guy is going to behave like that guy, this guy is going to behave like that guy. You know, if I swap these guys will swap, right? It turns out if I sort of impose a function that gives us this respect to this basis, it turns out it'll be a linear transformation, which we'll get to later in chapter 4. And what that means is these two guys are interchangeable. I can sort of think of V as Rn in this case.
What's the last word after 1 to 1 and? Onto?
Onto. O-N-T-O. Right?
Yeah.
Just one-to-one and surjective, or injective and surjective. Which I briefly explained in the first 3 lectures, but we'll get back to that later. So that's some implications. Okay? So as long as my basis, where this means my basis, if I take the size of that, it has n vectors in it, I'll be able to represent that in terms of Rn. I can think of these guys as interchangeable. And basically what this is, ultimately what we'll be able to say is, I don't know if I'll be able to talk about dimensions today. Probably not. But in the next class we're going to talk about dimensions, which we're going to be defining as the number of elements in a basis for the vector space. And basically what this will imply is that any n-dimensional vector space is indistinguishable from Rn, right? So any vector space where you are using, you can get a little more general, any vector space where you are using a field that has the same number of elements as the real numbers, such a vector space will be indistinguishable from Rn, as long as you can have n basis vectors to that vector space. Which means everything I know about Rn, I will automatically know about that vector space. Which is pretty cool, because we know a lot about Rn. We spent the last 3 semesters talking about Rn. And we know how to do calculus in Rn, all sorts of nice little neat things we can do in Rn. And it turns out that if I'm seeing another vector space, we can do a lot of those things, or at least approximate a lot of those things.
Professor,
Yeah.
question. So those are coordinates with respect to the bases, right?
With respect to the basis.
And then that just transfers it back to the real.
Right. So that means if I think of the basis as ordered v1, v2, all the way to vn, then my s, if I express in terms of these bases, c1, v1 plus c2, v2 plus cn, vn. Then if I just take all the coefficients of the guys and put them in a coordinate, and think of that as a coordinate in Rn, this can be done in exactly one way, which means this guy and this guy are interchangeable. I can call this by that name, no one would know the difference.
And that and this thing is the matrix, right? That
What is a matrix?
well, like the arrows you're implying that there's
This arrow represents a function that I'm thinking about, and the function is
that matrix.
to create this linear combination. So the function would be something like, it takes a rule, remember a function is just a rule that takes guys in one set called the domain, outputs to a guy that's in the codomain. If I make the rule to be, express this vector as a linear combination of the basis, the output would be that guy. Turns out that output would be unique, and it'll be done in a one-to-one and onto manner.
That function's the transformation matrix.
I would be able to represent that function as a linear transformation ultimately, and we can even generalize that as well. But that's just a little foreshadowing of where we're going to go. Once we deal with the last part of chapter 4 and chapter 8, this will start to make a lot more sense. But I just want you to start thinking about some consequences here. It'll also make a lot more sense after we talk about dimensions. Another thing that's another implication. And this sort of comes from our geometric interpretation of Rn. We can think of coordinates as locations. There's a specific address for each vector, right? I can imagine that, of course can't imagine if it's higher than dimension 4, but you can kind of imagine that, okay, this vector in my vector space, he will live somewhere in Rn, especially if it's R3, I can pinpoint exactly the location where this guy's going to be hanging out. So we can put on geometric interpretations to this as well, and think of X as being located at some point in Rn, and then we can start to do geometrical manipulations with that as well, so that's nice, right? So the implication is, ultimately, we have to do a little more work to show this, really, but ultimately I can think of any n-dimensional vector space as equivalent to Rn, and I can think of each vector as living in a certain location, and that gives me geometry. This gives me pretty much everything I know how to do with Rn. So it's a very, very, very useful thing. Let's move on to some specific examples here. Let B1 equals the I vector and the J vector. B2 equals 1 minus 1, 1, 1. B3 equals 1 minus 1, 0, 2. Note, these are bases for R2. The reader can verify. I'm just going to tell you that those are bases. With respect to the standard operations. And here's a question. Find the coordinates of x equals to 4 with respect to each basis. That's going to be the first thing we're going to do. E. Which x in R2 will have coordinate x subscript b2. That means the coordinate is with respect to b2 of 0, 2. So let's say that was a question. I said, okay, consider our vector space to be R2 with the standard operations. And I give you a random coordinate in R2, 2, 4. Find its coordinate with respect to each of these bases. Let's do A part 1. X with respect to B1 would be equal to C1 times, this would be C1, C2, where my x must be able to be written as C1 times I plus C2 times J. This means x with respect to B1 would be what coordinate?
2, 4.
It's itself. So that one was easy. Let's look at the second one though. In this case, we'll set x to be C1 times this vector plus C2 times that vector, and I want to find C1 and C2. This means I need 2, 4 to be equal to 1, 1, minus 1, 1 times C1, C2. And so what I have to do is I have to solve this system. Since this is a basis, we didn't verify, but I told you it's a basis. I mean, when I find the reducer echelon form of this system, this guy matrix reduces to. What is that going to reduce to? What will be the reducer echelon form?
Reduced row echelon form, you said?
Mm-hmm.
1, 1, 2, 0, 2, 6.
No. Reducer echelon form. Well, the left side should be able to tell me automatically.
1, 0, 0, 1.
Right. It has to be the identity. Right?
Minus 1.
Why? Because I know if I threw in 0 here, it has the unique solution, which means this matrix here must be invertible, which means this reducer echelon form is the identity. Turns out that if you actually went through and do the calculations here, I think I actually did them, you'll get minus 1 and 3 as the answers here, which means x with respect to B2 has coordinates minus 1, 3. So x changes its location, right? If I think of it in terms of this basis, that's its address. If I think of it in terms of this basis, that's its address. Similarly, for A3. Similarly, for x x with respect to the third basis, we need to solve 1 minus 1, 0, 2 equals to 4. Find the reduced or echelon form of that. I know the left side has to be the identity because it's linearly independent. And so it would have the unique solution, and that actually became 2, 3. So if I look at my vector with respect to the third basis, this is actually going to be the location 2, 3. In other words, what I'm saying is the vector 2, 4 is actually 2 times this vector plus 3 times that. And we had another part. Let's say x with respect to 3 is 0.2. What was x? Well, basically x in terms of the standard basis. This means, what is x? Well, that's the coordinate for x with respect to B3, meaning that's the coefficient of the vectors in the basis B3, which means this is going to be 0 times 1 minus 1 plus 2 times 0, 2. Or did I ask B2? I think I said B2. Which was this and that. So that's just going to be the vector 2, 2. So if I express this coordinate in terms with respect to basis B2, that would be the answer. With respect to the standard bases, what are the coordinates of this matrix? This polynomial. Of course, it has to be the requisite vector space. Here we're assuming V is M22. Here we're assuming V is P2. We'll end there, think about that for next time, and then we'll continue. We're pretty much done now. I'll mention a couple more things about the bases. Then we'll move on to dimensions.
I had a quick question. This is going to go into it. Why is
Yes, hold on, let me stop.
Sure, sorry.